Rational functions. Objectives. Use arrow notation to describe end behavior of rational functions. Find the domains of rational functions. Identify vertical and horizontal asymptotes of graphs of rational functions, and graph rational functions. Rational functions. A function of the form f of x equals p of x over q of x, where p of x and q of x are polynomial functions with q of x not equal to 0, is a rational function. Notice, a rational function is a fraction of polynomials. Also, any polynomial is also a rational function. We can describe 3x cubed plus 5x plus 1 as 3x cubed plus 5x plus 1 all over 1. Manipulating the equation form of a rational function. At times, you may be given a form of a rational equation that has been split up in some way. It can be helpful to combine the expressions so that you can use the same graphing techniques as on the other rational equations. Let's practice here. Combine the expressions on the right side of the equation in order to make the right side a single rational expression. Here I have y equals 1 over x minus 2 minus 4. I'm simply combining these fractions. 4 has a denominator of 1, and I need to have a common denominator of x minus 2 in order to combine those. So I'm going to multiply 4 by x minus 2 over x minus 2. This will give us 1 over x minus 2 minus 4 times x minus 2 over x minus 2, which is 1 over x minus 2 minus 4x minus 8 over x minus 2. And one last step, y would equal 1 minus negative 8, which is 1 plus 8, a 9, minus 4x all over x minus 2. Definition of a horizontal asymptote. The line y equals b, where b is a constant, is a horizontal asymptote of the graph of f if f of x approaches this constant b as x approaches either positive infinity or negative infinity. A horizontal asymptote is a type of end behavior. In this graph, as x approaches negative infinity, y approaches positive infinity. But as x approaches positive infinity, y approaches 2. This shows we have a horizontal asymptote of y equals 2. A graph can definitely touch a horizontal asymptote. Vertical asymptotes. The line x equals k is the vertical asymptote of the graph of f if f of x approaches infinity or f of x approaches negative infinity as x approaches some constant k from either the left or the right. Now, a rational graph cannot touch a vertical asymptote. We'll see this more as we continue with the lesson. With this first graph, we can see as our graph is approaching this certain k value, it starts to where it is approaching negative infinity. If we're approaching this certain value from the right-hand side, then our graph begins to approach positive infinity. So we can see we have a vertical asymptote there. The same thing on the second graph. As we're approaching a certain constant value of x from the left-hand side, y is going up to positive infinity. And if we're approaching that value from the right-hand side, then our graph is approaching negative infinity. Same with this. And on our third graph, let's say maybe this is the value 3. As x is approaching the value of 3, y is approaching negative infinity from the left and positive infinity from the right. These are all vertical asymptotes. We can also have an oblique or slant asymptote. An oblique or slant asymptote is a diagonal linear function that a function is close to for very large positive or negative x values. The end behavior of this function is as x approaches negative infinity or as x approaches positive infinity, we are getting close to this line of y equals negative 3/4 x plus 9/4. So this is your oblique or slant asymptote. Determining end behavior of a function. Let's determine the end behavior of these rational functions. The first one, y equals 7 over x plus 1. When we talk about end behavior, we're looking at when x approaches either positive or negative infinity. What's going on? When this gets to be a very large x value, let's say 1,000,000, we would be saying 7 divided by 1,000,001. As we get larger and larger and larger values of x, this becomes even smaller. So as x approaches positive infinity, y approaches 0. So the end behavior is that we have a horizontal asymptote of y equals 0. Beyond this, we can try a different type of strategy. Remember, this is a rational function where the top polynomial is being divided by the bottom polynomial. So let's go ahead and divide this. I have 2x squared plus 0x plus 1 being divided by 6x squared plus 7. So 2x squared divided by 6x squared is going to be 1/3. 1/3 times 6x squared is 2x squared, and 1/3 times 7 is 7/3. Now I'm going to subtract those. The x squareds go away. 0x, 0x. 1 minus 7/3, I'm going to have a negative 4/3. So an alternative way to write this function would be y equals 1/3 plus a negative 4/3 over 6x squared plus 7. Isn't that right? Now, if we think about when x is approaching either positive infinity or negative infinity, we want to talk about when x is getting to be very large values. This denominator of this fraction will get very large, causing that fraction to approach 0. And we're left with just this 1/3 in front. So, as x approaches positive infinity or negative infinity, as it were, we have a y that's approaching 1/3. Or in other words, our horizontal asymptote is y equals 1/3. With this rational function, I can work the same type of way, but I know that alternative way to write that function is going to be 0 plus 3x plus y over 2x squared plus x, because this numerator is too small to be divided by 2x squared plus x. So it goes in 0 times, and this is, well, that's our remainder. As x approaches infinity, this bottom of the fraction is going to grow so much quicker than the top that eventually this approaches 0. Plus the 0 that we already have. So as x approaches positive infinity, y is approaching 0. In other words, our horizontal asymptote is y equals 0. For this rational function, the top is large enough to be divided by the denominator. So let's try to carry out that division. 3x squared plus x plus 0 divided by x plus 1. 3x squared divided by x is going to be 3x. 3x times x plus 1 is 3x squared plus 3x. Then I'm going to subtract that. 3x squared minus 3x squared is now gone, and I have a 1x minus 3x is a negative 2x plus 0. And we try our division again. Negative 2x divided by x is negative 2. Negative 2 times x is negative 2x. Negative 2 times 1 is negative 2. And I'm going to subtract this, which changes our signs. Negative 2x and positive 2x drop out, and a 0 plus 2 is 2. So the alternative way of writing this would be 3x minus 2 plus 2 over x plus 1. Again, what is the end behavior? As x approaches positive infinity, this is going to go to 0. But we're still left with this, and that is not a constant. So, as x approaches positive infinity, y approaches 3x minus 2. That's not a constant, and it's definitely not a horizontal line. This is an oblique or slant asymptote. So our oblique asymptote is y equals 3x minus 2. Now this long division process, or synthetic division if it applies, will always work with finding those asymptotes. Let's summarize the end behavior of a rational function. Basically, what we could do is compare the degrees of the top and the bottom. If the bottom is larger, then the horizontal asymptote is going to be y equals 0. If they are equal, then we can simply divide those lead coefficients for the horizontal asymptote. If the top is larger by 1 degree, then we flat out have to divide the polynomials, and that quotient will be an oblique asymptote. Hopefully now we can see that horizontal asymptotes and oblique asymptotes, they're mutually exclusive. You will have one or the other, not both. Vertical asymptotes in equation format. Now, if a factor remains in the denominator even after simplifying, it is an infinite discontinuity and a vertical asymptote. Now, we also have things called holes. A more technical term for a hole is removable discontinuity. If a common factor can be removed from the numerator and denominator, it is a removable discontinuity and creates a hole in the graph. Now let's look at how this appears in equation format, this whole idea of holes or vertical asymptotes. For a rational function, the numbers missing from the domain come from the holes and the vertical asymptotes. Determine any vertical asymptotes or holes in the graphs of, we have this first function, it's already factored for us. We can see that the numbers of -1 and 2 would have to be excluded from the domain. Now, the number 2 is removable. This means that we have a hole here. There is a hole when x is 2. This is equivalent to 1 over x plus 1 with the added condition that x cannot equal 2. Now, what is the y when x is 2? 2 plus 1 is 3, so we would have the point 2, 1/3 is where our hole in the graph is. The other x equals -1 is a vertical asymptote. Over here we have no removable discontinuities. We have just this x minus 2 in the denominator. So our domain restriction is that x cannot equal 2. For holes, there are none. And vertical asymptote of x equals 2. This function here, 3 factors on top, 3 on the bottom. I have a removable discontinuity here and another removable discontinuity here. So my domain is going to be all x's except that x cannot equal 1, 2, or 3. I have a hole at 1 something and another hole at 3 something. Remember, holes are the removable discontinuities. I have a vertical asymptote and x equals 2. Now let's go ahead and write the simplified version of this. This would be the same as the function x minus 4 over x minus 2, where x cannot equal 1 or 3. Now, if x were 1, we would have a -3 on top, we would have a -1 on bottom, so a -3 divided by -1 is +3. I have a hole at 1, 3. And if x were 3 on top, I would have a -1 on top and a 1 on the bottom. So a -1 divided by 1 is -1. This last one, we have to do a little bit of work. It's not quite factored for us. I'm going to factor out the 3 on the top, and then I have fully factored form. I can see my domain. It's going to be all real numbers except for 2 and 3. What do I have in the way of holes and vertical asymptotes? Well, here I have a removable discontinuity. So I do have a hole when x is 3. Let's write this in its simplified form. 3 over x minus 2, where x is not equal to 3. My vertical asymptote is going to be x equals 2. And let's see what the y part of the hole is. If we put a 3 into our simplified form, it would make the denominator 1. So 3 divided by 1 is 3. Now let's get to graphing all these pieces so we can kind of tie these concepts together. Let's graph the rational function y equals 2 over x minus 3. Let's first find the x-intercept. Remember, an x-intercept is when we make y 0. So 0 equals 2 over x minus 3. If I multiply both sides by x minus 3 to clear the fractions, the left side will still be 0, and the right side will be 2. And 0 does not equal 2, so I don't have an x-intercept. Let's try to find a y-intercept. The y-intercept is when x is 0. So if x is 0 here, then y is going to be a negative 2/3. So the y-intercept is 0, negative 2/3. Are there any holes? I don't see any common factors in the numerator and denominator, so there are no holes. I do have a non-removable discontinuity when x equals 3. So x equals 3 is my vertical asymptote. My horizontal asymptote, well, my numerator is of smaller degree than the denominator. Or if I would go ahead and perform division, I would see that this is y equals 0 plus 2 over x minus 3, or y equals 0 is simply the horizontal asymptote. Is it possible that we could cross the horizontal asymptote? In other words, is there an x value when y equals 0? Well, we already tried that up here for x-intercept. X-intercept is when y is 0, and y equals 0 happens to be our horizontal asymptote, so it's not going to cross the horizontal asymptote. There's no oblique asymptote because we have a horizontal asymptote. Now, you don't always need a sign chart to be able to graph these, but I think it's a good idea to stay in practice. So let's go ahead and make our sign chart and see how it corresponds with the graph. We have one critical value of 3, and our factors are 2 and x minus 3. 2 is always a positive number wherever we are. Let's test 0. 0 minus 3 is negative, and a positive times a negative is negative. Let's try testing 4 in this right interval. 4 minus 3 is positive, and a positive times a positive is positive. So let's go ahead and graph the certain features we have. No x-intercepts, a y-intercept of 0, negative 2/3. We have no holes. We have a vertical asymptote of x equals 3. We have a y equals 0 for our horizontal asymptote. Some people like to just float that right on the surface of that x-axis if it happens to be y equals 0 so that you can still see it. No oblique asymptote. And now we start our graphing. I know I'm going to have to start from including this point that I have. As x approaches negative infinity, y is approaching that horizontal line. And as x is approaching 3, y is approaching negative infinity here. Now this is where the sign chart might come in handy. The sign chart says to the left of 3, our graph is always negative. It's always below the x-axis, and I can see that here. On the right side, it says we're always above the x-axis. So that means that our graph must do something like this rather than something like this. And we have a good sketch of our graph here. With this next function, we've been given something that is an expanded form. I'd like for us to first factor it so we can see what it's made of. Always a good idea to have both of the forms, fully expanded and fully factored. So here we have, find the x-intercept. My x-intercepts, as we saw before, is where we make the y equal 0. Well, we end up where it's always the zeros of the numerator. So we have a negative 1/2, 0 for the x-intercept. Y-intercept is where we make the x's 0, and it helps to use the expanded form there. If the x's here are 0, then y is 1/2. Now let's look for holes. I don't see any factors that are common in top and bottom to be able to remove. That means I don't have holes in this graph. For vertical asymptotes, both of the factors that are in the denominator are going to give us the vertical asymptotes. So an x equals -4 and x equals -1. A horizontal asymptote, if we were to divide this, maybe with long division, the numerator is too small to divide. It goes in 0 times. So the horizontal asymptote is y equals 0. Now, does it cross the horizontal asymptote? In other words, is there an x when y equals the 0 that we said? Well, it does, and we found that already as the x-intercept. So yes, it crosses at a -1/2, 0. We have a horizontal asymptote, so we do not have an oblique asymptote. Remember, those things are mutually exclusive. A sign chart. I think it'd be a good idea for us to have a sign chart here. Let's list all of our factors to the left. And then we're going to have 3 critical values from the factors that are given. We have a -4, a -1, and a -1/2. Now to test each interval. -5, well, 2 is always positive. -5 times 2 is -10, plus 1 is negative. -5 plus 4 is negative. -5 plus 1 is negative. And so this is negative. Let's try a -3 here. 2 is always positive. 2 times -3 is -6, plus 1 is negative. -3 plus 4 is positive. -3 plus 1 is negative. And here we have an even number of negative signs. We're going to have a positive interval here. Let's try a -3/4. 2 is always positive. 2 times -3/4 is -3/2. -3/2 plus 1 is still negative. -3/4 plus 4 is positive. -3/4 plus 1 is positive. And we have an odd number of negative signs, so this interval is negative. One last interval to check. Let's test 0. 2 is always positive. 0 plus 1 is positive. 0 plus 4 is positive. 0 plus 1 is positive. This is a positive interval. Now let's graph the features we have. I have a -1/2, 0. I have a 0, 1/2. There are no holes. I have x equals -4 as a vertical asymptote. And I have x equals -1 as a vertical asymptote, and y equals 0 as a horizontal asymptote again. And we already have that crossing point there on the horizontal asymptote. So it's a good thing we have our sign chart because we don't have a lot to go off of here. To the left of -4, I know my graph is always below the x-axis. That means we're going to have a graph that looks like this, where the ends are pulled towards the asymptotes. Between -4 and -1, we're always above. So we'll have something like this. Now we don't really know the exact shape in this area, and we don't know how low or how high it goes. We would have to have some calculus for that. But remember, this is just a sketch. Just as long as we're showing that it's above the x-axis and has some kind of a shape similar to this, we're okay. Now, between -1 and -1/2, we're always below. So here we are and getting pulled toward the asymptote. And after 1/2, we're always positive. But remember, you have to get pulled toward the asymptote. So we get pulled back down that way. Now let's graph y equals x squared minus 4 over x. The x-intercept, remember, is by finding the zeros of the numerator. So we have, in factored form, x plus 2, x minus 2 over x. And that would give us x-intercepts of -2, 0 and 2, 0. Y-intercept is when x is 0, so these terms would go away. I would have -4 divided by 0, which is undefined. That means I don't have what I'm looking for. I don't have y-intercepts for this. Do I have any holes? Any common factors in the top and bottom that could be removed? No. A vertical asymptote? Of course, at x equals 0. A horizontal asymptote? Let's try to divide. X squared plus 0x minus 4 divided by x. So x squared divided by x is x. X times x is x squared. Subtract, and I'm going to have just a -4 left. -4 can't be divided by x, so our alternate form is y equals x plus -4 over x. And when I'm looking at that, I see as x approaches very large numbers, this will go to 0 and we're left with x, which is not a constant, so it's not a horizontal asymptote, but we do have an oblique asymptote of y equals x. X-intercepts, -2, 0, and 2, 0. No y-intercepts to graph, no holes. I have a vertical asymptote of x equals 0. And this oblique asymptote of y equals x. Now, let's go ahead and do a sign chart just so that we can be consistent with how we've done the others, and so we can see how it works when we have an oblique asymptote as well. I have 3 factors to show. I'm going to have 3 critical values to place there, and I'll have 4 intervals to test. Let's test a -3. -3 plus 2 is negative, -3 minus 2 is negative, and -3 is negative. So this is a negative interval. Between -2 and 0, let's test a -1. -1 plus 2 is positive, -1 minus 2 is negative, and -1 is negative. An even number of negative signs means I have a positive interval. Let's test here, maybe a 1. 1 plus 2 is positive, 1 minus 2 is negative, and 1 is positive. We have an odd number of negative signs, so a negative interval. To the right of 2, let's test a 3. 3 plus 2 is positive, 3 minus 2 is positive, and 3 is positive. We have no negative signs, so this is a positive interval. So how does that play out when we have our graph? To the left of -2, we're below the x-axis, getting drawn towards that oblique asymptote. Between -2 and 0, we have above the x-axis, getting pulled towards that vertical asymptote. Between 0 and -2, we're below the x-axis, getting pulled towards that vertical asymptote. And to the right of 2, we're always above the x-axis and getting pulled towards that oblique asymptote.